In this video, we begin to discuss the reactions of oxygen nucleophiles with carbonyl groups, something that will occupy our attention for several videos. So to start with, I would like us to consider what would happen if a neutral alcohol serving as a nucleophile were added to a neutral carbonyl compound. Okay, so an example of that would be the addition of an alcohol such as methanol to acetone. Well, in step one of the mechanism, the lone pair on the oxygen attacks the carbonyl carbon, and we at the same time break the CO pi bond. Well, looking at the product of this step in the mechanism, you can see that when you're starting with a neutral alcohol, that oxygen that was on the alcohol now has a positive charge on it, and the oxygen that was the carbonyl oxygen now has a negative charge on it. This will not happen. This is not a reasonable step in a mechanism because we are starting with two neutral molecules and we are generating a single molecule that has a strongly acidic and strongly basic site. Remember that any oxygen atom that is forming 3 bonds and has a positive charge, if there is a hydrogen on that oxygen, it will be a highly acidic hydrogen, a pKa of -2 or -3. And similarly, an oxygen forming 1 bond that has a negative charge is a pretty strong base, such as hydroxide. Its conjugate acid pKa is going to be about 16. So you're not going to have a step in which you generate a strong acid and a strong base in the same step, period. You especially will not have a step where you generate a strong acid and a strong base in the same structure. Okay, another way to think about this phenomenon is that the neutral alcohol is not good enough nucleophile, and the neutral ketone or aldehyde is not a good enough electrophile for the reaction to take place. Furthermore, as if that wasn't bad enough, entropy works against this step too, because in this particular step of a mechanism, you've got 2 molecules coming together to produce 1. Now that happens in many steps of mechanisms that are okay. What I'm just saying is that the delta S term also contributes to an incredibly large delta G term for this step. Because when you take 2 molecules and bring them together to make 1, that is a decrease in disorder. Okay, so what can we do to activate one of these molecules? Well, there's 2 options. We can make the nucleophile more nucleophilic, or we can make the electrophile more electrophilic. We will look at both of these in turn, but we're going to start by looking at option 1, making the nucleophile more nucleophilic. So the way we do this is instead of using neutral methanol as the nucleophile, which if you think back to our discussion on nucleophiles, a neutral alcohol was listed as a C nucleophile, we're going to use an anionic nucleophile, sodium methoxide, NaOCH3. Having a minus charge, it is a much better nucleophile. Okay, so let's look at the mechanism here. So in the first step, just like what we talked about earlier, we have nucleophilic attack of OCH3 minus, but the product after this step has just a negative charge on the oxygen that was formerly the carbonyl oxygen. Because we started out with OCH3 minus, the alkoxide oxygen, now that it is forming 2 bonds, is neutral rather than positively charged. Okay, and then the second step is proton transfer from solvent. Okay, so this reaction with sodium methoxide is taking place in methanol as the solvent. In fact, you can buy from a chemical supplier a 21% solution of sodium methoxide in methanol that is commonly used as a one-pot reagent for these types of reactions. So the methanol in there then serves as the proton source to generate a neutral alcohol product in the second step of the mechanism. This is exactly the same as the second step of the sodium borohydride mechanism, where in that case we usually do those reactions in ethanol rather than methanol, but we have proton transfer from the solvent to generate a neutral product. Okay, this product, where you have an OCH3 and an OH bound to the same carbon, if you think back to your lesson on functional groups, is called a hemiacetal, and this reaction overall is called hemiacetal formation. In this case, we are doing it under basic conditions. In a couple of videos, we will revisit this under acidic conditions. Okay, so a couple of notes on this reaction. First of all, the proton transfer from the methanol solvent, as you can see, regenerates OCH3- as what may be thought to be a byproduct in this reaction. But the molecule of OCH3- that is generated can come back and react in step 1 with another molecule of ketone. In other words, OCH3- does not actually get consumed in this reaction overall because more is generated at the end of the mechanism. Therefore, only a catalytic amount of the base of OCH3- is necessary. You know, if you had only 0.1 moles of OCH3- for a full mole of ketone product, assuming you have plenty of methanol as a solvent, which is always true in a reaction, the reaction will go because the OCH3- continues to get generated at the end of the mechanism. Okay, so now in terms of the equilibrium for this reaction, we have an alkoxide, which is a fairly strong base at the beginning of the mechanism, but we have an alkoxide, which is still a fairly strong base, at the end of the mechanism. So this reaction is not generating a weaker base. So based solely on the strength of the base, delta G should be about 0 for this reaction. Therefore, the reaction will take place, but it will be reversible. Okay, so this reaction can go forwards or backwards. Delta H considerations favor the forward reaction because the CO pi bond is replaced with a stronger CO sigma bond. So in terms of strictly bond energies, it's going to want to go towards the right. However, delta S considerations are going to favor the reverse reaction because, as we've already said, in the forward reaction, two organic molecules, are becoming one. Okay, so we say that delta G is close to 0. What we still need to consider is, will delta G be slightly greater than 0, truly be 0, or slightly less than 0? And the answer to that question actually depends on the exact identity of the carbonyl group. Okay, whether it's an aldehyde, formaldehyde, or a ketone. And we will come back and discuss this topic in a more general sense, the relative reactivities of aldehydes versus ketones, in the next video.